Hi everyone, I am Maria, not Maria, Maria, and I am an associate professor at the Aeronautics Institute of Technology. And I'm here to present a framework we developed for vehicle routing problems, and it's called AILS. We compete on DIMACS challenge. We got the third place with this framework. We have some variants of this framework, and we refine, and I will show the refinement, the results of the refinement of AILS. And this is work that we have the Vinicius. Vinicius is the one who implemented. He was my PhD student. Now he is already a doctor. And Jean-François Courdeau, who started to work with us after the first paper was published. Here's an outline of the talk. First, I will present the framework AILS, that is an iterated local search-based meta-heuristic, but with an adaptive mechanism that tries to control the diversity of the method. Then I will present the results of the three methods that we developed. One is a hybrid version of AILS with path relinking, and it was developed for the CVRP. The other version is an AILS for the heterogeneous vehicle routing problem. We already published these two results. And the last one is the one that we refined and now submitted. It's for large-scale instances. We focus on this type of instances and for the CVRP. And then I will present some results of this framework for the allocation problem, the maximum coverage location problem, and then present some remarks and future work perspectives. Well, this research started when Vinicius came to me and asked what would be a challenge problem to approach by a meta-heuristic. He wanted to investigate the diversity control of iterated local search. And then I suggested a vehicle routing problem. And he is crazy enough to investigate the capacitated vehicle routing problem. And it took him 2 years to achieve the version he presented first. That is the one that published in EJAR. And then he refined this version, and I will present some of the refinements here. But the iterated local search, for those who doesn't know, is a local search-based meta-heuristic applied successfully to a wide variety of combinatorial optimization problems. And it has two phases. Broadly speaking, it has two phases. The perturbation phase, we perturbate the solution, and then we apply a local search phase to the solution. And there is an acceptance criterion to check if we use this solution as a reference for the next iterations. And a pseudocode of this method is here. We have the perturbation procedure and local search procedure, and then we apply the acceptance criterion. And for AILS, I'll show and come back, we differ from iterated local search by these two lines highlighted in red, where we updated the diversity control regarding the perturbation degree, how much we perturbate the solution, and an updating of the acceptance criterion, also both focus of these diverse control mechanisms. So what is the perturbation degree? The perturbation degree is the number of change applied to the reference solution. So how far we will let the method to perturbate the solution. And the acceptance criterion, most of the studies of iterated local search accept the solution if it's better than the reference. But some studies show that if we apply some threshold that is not that hard, because it's hard to achieve a better solution when you are in the advanced iterations, then we could achieve a better results if we relax this threshold. And this was the 2 points he studied in his PhD. And the first version of AILS is a hybrid version with path relinking. And the difference between AILS and AILS PR is that we update an elite set of solutions, and then we apply a path relinking between the solution found in the iteration and a elite set. That's the difference. The perturbation degree strategy is here. I will just talk briefly because there are many parameters. And the idea is to diminish the perturbation degree is this parameter here, omega. And it is related to the removal heuristic in the case of the routing problems. When we perturbate the solution, we remove nodes from the solution and then insert it back in other routes. And in this case, the perturbation degrees is the number of removal nodes, the nodes that should be removed from the solution. And if we have an ideal instance, that is this parameter, d beta, we want to adjust this perturbation degree in such a way that it is, if the ideal instance is much higher than the average instance between the solution found during the iterations and the reference solution, this is the DHR. If the difference is too high, and these are greater, then I want to increase the perturbation of my method. If the average distance is lower, is higher, then I try to decrease the perturbation degree. So the method, the strategy is this. That's how it works. And we have 3 versions of AILS. And one of the differences, they differ in the insertion heuristics, the removal heuristics, but one of the differences is this ideal instance, how we set this ideal instance. And the acceptance criterion that I told that it was a threshold, we set that threshold. We accept the solution only if it has a quality better than or equal this threshold. And it is the sum between the best overall solution in the last iterations plus an 8, here that is eta, multiplied by this difference, that is the average solution minus the best solution over the last iterations. So we have also a difference in among the 3 versions of AILS. We approached this parameter in a different form. Here's a table summarizing the strategies that we use it to set these parameters. The first version of AILS, that is this hybrid version for CVRP, we use a fixed value for the beta, as well for AILS for the heterogeneous vehicle routing problem. And for this last version of AILS, we use the convergent criterion that I will not go into detail here, but if someone is interested, I can talk about it later. And this parameter here, we have an adaptive criterion in the AILS for the CVRP, the first version, a fixed value for the HVRP, and a convergent criterion, again, a convergent criterion for the CVRP. And this one is for large-scale instances, okay? And another difference that when we designed the AILS for large-scale instance, we noted that when we exchanged swap by swap star, we achieved much better results, so we employed that in this last version. First, I will present the results of CVRP and the first version AILS-PR. We published these results in this paper. Here we didn't have the collaboration of Courdeau yet, but we tested AILS-PR with the 100 instance, the X instance proposed by Shaw and collaborators, and we test and compare with these three other algorithms, that's state-of-the-art for the CVRP. We had that all four methods were run 50 times for each instance, and we employed this stop criterion to achieve the same comparable time among the four methods. What we report here is the gap between the values of the average solutions and the best known solutions. With this method, we improved some best known solutions that we report in the paper. To summarize the results, we separate the instance, the X instance, in three classes. The first one are the smallest one with up to 250 nodes. And the second class has up to 500 nodes. And the last group is the largest one with the largest number of nodes with 500 to 1,000 nodes. So we separate the instance in these three groups. And here are the statistics of the results. First are the statistics of the average gaps, of the best gaps, and then the average times. We can see that AILS-PR had the best results here and here. And for this last case, series had the best maximum, average maximum solution, but we had the best minimum and mean. Most of them were 0 in case of the minimum, but we can see that our intervals of the results were tighter than the other methods. And the times were very comparable. All the methods had similar times. And now I will present the version for the HVRP. We published this study in Computers and Operations Research. We had collaboration Courdeau in this paper. And we tested 12 instances. And we compared with 2 AILS and UHGS. And here is the stopping criterion. Also, we try to keep the times very close to the other methods. The variants we tested because we have many variants for the heterogeneous vehicle routing problem. So we tested these 5 variants and that differ from limited fleet, fixed costs, and dependent costs. And as UHGS tested for these 3 variants, I will present here in the paper have the results of the 5 variants, but I will present here these 3 cases to show the results of the 4 variants, the 4 algorithms. And I want to highlight that this code was in Java, that it's not the best programming language, but the Vinicius, the one who developed the framework, felt more comfortable in developing this language, and I think he achieved a very good framework even with this disadvantage of the language. Well, here, better there. We have that AILS, this is not a hybrid version, got the best average gap among the 4 methods. Here, this one is for this variant of the heterogeneous vehicle routing problem. For this variant, in the 3 variants is unlimited fleet. We have also the best average gap. And the I think the time was, this one is better. And in this last case, AGS was better on average, but we had a close average gap here. And finally, the third version, the latest version of AILS, it was initially designed for large-scale instance, and we competed on DIMACS challenge with the name AILS2. And the reason is because it had two phases. It had a structure that differed from AILS, and then we changed it. After the challenge, we changed the framework in order to achieve the same results using the idea that we had for achieving the better results for large-scale instances. And then we refined it, and now we are using AILS because it just differs on parameters, movements, and insertion heuristics. So in this case, with AILS, we got the third place, first place for large-scale instances. I was talking to Eduardo, and we comment that it achieved the best gaps in the cases, and the fact that it was designed for large-scale instances, and the wait on time, I think the indicator parameter that it was used to see which method was better than the other was the factor that we got the third place. And one observation is that this method was done from scratch. And it took a long time for him to achieve these results. And I think it gives us new insights about the problem. And I think I am a proud mom. So I think that my student made a really good job. And this is the latest version of the method. Here we have two experiments. The first experiment, we compare AGS and Philo on the X instance, the 100 instance proposed by Uchoa. We ran, I think he ran both algorithms in the same machine. So he ran 50 times, each of them, including AILS. And in the second experiment, we compared just with Philo, because we talked to Thibault, and we decided not to include in these experiments because the algorithm AGS was not designed for large-scale instance yet. Yeah. So here is the results of the first experiment. We have this line, the results of AILS, this line, the results of HGS, and this one of the Philo. So we have here that our method kept the 0.1 gap. It was really very stable for these X instances. And for large-scale instances, we achieved better results on average and for each instance too. There is one case here that the best result was achieved by Philo. We improved some BKS too. I think we reported just for Eduardo, who keeps the web page. And then I will briefly talk about AILS to allocation problem. We're expanding the application of the framework, and we tested for a classical location problem that is the maximum covering location problem. And its goal is to find the P facilities that the sum of the demands of the customers are within a covered ratio. And we compared the results with the current method that is designed for large-scale instances. And because for a small instance, there is no sense to apply heuristic methods because the solvers solve these problems very fast. So there is no reason to use for small instances. The literature has 24 instances and we use all of them. We report the average gap and the gap to the BKS, and this is the stop criterion. We had 30 independent runs. And we have a pure version without any hybridization and a hybrid version with path relinking. And you can see that this hybrid version achieved the best results. It had a very low average gap in comparison to the other versions. And both versions of AILS, as for the location problem and for the large-scale instance, are submitted to journals already. Here are some remarks. We developed 3 versions of AILS for vehicle routing problem, 2 of them for the CVRP. One is a hybrid version that fitted better for small and medium-sized instances. It didn't scale well. That's the reason why we developed the other version for large-scale instance. And this is the latest version that I discussed here. We have a version for the heterogeneous vehicle routing problem and another one for a location problem. And as future works, we are trying to code our AILS in C++. I need hands there, but now I think I found some hands to do that. And we also want to explore other variants of VRP. And this one is questionable because the more robust learning technique you use, more time-consuming the method become. So we are trying to balance this, but we are trying to put more elegant learning strategies to adjust some parameters of the method. So I would like to thank the organizers for the invitation. And that is it, I think, yes.
Yes, hello Maria. Excellent work. Thank you for the presentation. I appreciate that you didn't include a comparison with HGS, for example, an instance with 20,000 customers. The reason indeed is that when we design or calibrate a code for 300 customers, you cannot just take it and apply to 20,000 without calibration. It doesn't make much sense. So I would be very interested to learn about your experience scaling a code to very large instances. What were the most critical design choices that allowed you to take a code that was very efficient for medium-scale instances and to bring it to deal with very large-scale instances?
All the credit is for Vinicius, not me, because we just had talks, and he was the one who developed the framework. However, what we learned, it was that the path relinking was very time-consuming for the large-scale instances. So we had to use that mechanism that had in path relinking, incorporate in AILS somehow, in order to avoid all that thing we need for keeping the path relinking phase in that hybrid version. So that's what we learned. We couldn't hybridize the method because it was too time-consuming.
And did you do a bit like in Philo, for example, when you have local search, try to keep the local search focused on certain customers that are activated to avoid running many loops on 10,000 customers and converging very slowly?
Yes, this version has this.
Okay, so that's a very critical strategy.
Yes, yes.
Is any version of the algorithm public?
Yes, this last one that is under review, you gonna release the public version, but we're just waiting for the reviews. But as soon as the paper is accepted, we'll release it.
of results that you presented, they were all run on the same computer?
Yes,
Okay.
but some of them, wait a minute. Here, this version, this version here were in the same computer.
The previous one?
The previous one, no, that's why I reported here the clock of the machines. For the heterogeneous, we used the values reported in the papers. Okay.
How did you convert the time? Because, for example, these results of UHGS, they were more or less from 2012. So there's worth, even if the clock is a bit the same, the computer is very different. So did you use some performance index?
No, we didn't use it. But when he tried to use another computer, and we saw that the clock was the one who would influence the method. But we didn't use the CPU benchmark, this kind of things we didn't.
Because the cache of the processor has also a large impact sometimes on the speed of...
Yes, that's true. But when what I remember from this paper is that he said that the machines that the other AILS, UHGS used were superior than the one he used. That's what he reported. Or comparable. But I think I think you are right. We should have done this more fairly. But we have just the disadvantage of the language already.
If I can add a little bit on this, it's kind of difficult to compare, especially with the older hardware, because if on one side considering frequencies is not very fair, because maybe the frequencies are very similar, but instead the system is quite more capable right now. But on the other side, when we consider like pass marker score, they consider only the processor. So if we look at our algorithm that usually are more memory bound,
Yes.
the memory didn't scale on the same way than the processor. So we are kind of we have two measures to scale our results, but there are neither of them is kind of taking all the components fairly.
Can you please show the next table, the graph?
This one?
Yes, this one. Yes, this. And so it looks that your method is quite stable from 200 to 1,000. You are increasing the time, the same time for all instances?
Yes, the same time.
The same time,
Yes.
For all methods, for all instances, you run for the same time.
Yeah, the criterion is not the time. It's here I didn't report. I think it's 40,000 iterations without improvement. So we didn't control the time, but the time was, here the time were very comparable among here we use the same machine.
Okay. And these, anyway, are the same machine, the modern machine?
Yes, the same. We use the same.
Looks pretty simple.
Yes. Here we use the same stopping criterion. We had the same times.
The first paper where you reported tables, you compared with the old result from UHGS. Did you try to compare with the newer results that were available in more or less 2021, 2022 of the new implementation of the AGS?
We didn't, but we are with this version. We are comparing. This is the new version of AGS. Because you hadn't published yet the paper, and we didn't use it.